Welcome to another deep dive here on our show. Today, we have some fascinating material that takes us on an incredible journey through technology. We'll go from super fast humanoid robots in Beijing to, imagine this, proteins functioning as quantum sensors inside living cells.
And there's more. Brain-machine interfaces using cultured human tissue, self-assembling robots, and we'll also delve into the dilemmas of deep-sea mining. Plus, a curious gadget in the midst of it all. Our mission here is to try and break down these innovations, to understand the science and engineering behind them, and, of course, what it all might mean for the future. Ready? Let's get started.
We begin in China, where the inaugural World Humanoid Robot Games just took place. And look, there was one robot, UNITREE's H1, that was the big star. It took home 4 gold medals, including in a 1,500-meter race.
Exactly. It was an impressive demonstration of agility, wasn't it? The humanoid won the 100-meter hurdles, the 400-meter, the 1,500-meter you mentioned, and even the 4x100-meter relay. The maximum speed it registered was 4.78 meters per second. That's over 17 kilometers per hour.
7 kilometers per hour! E a UNITREE já fala que está testando modelos que passam dos 5 metros por segundo. Isso em laboratório, claro. Outra empresa que se destacou foi a Humanoid com o robô Tiankung nos 100 metros rasos. Puxa vida, quase 18 km por hora para um humanoide correndo. O que permite essa velocidade toda? Não é só força bruta, imagino, né?
17 kilometers per hour. And UNITREE is already saying they're testing models that exceed 5 meters per second in the lab, of course. Another company that stood out was Astrobot, with its S1 robot in the 100-meter dash. Wow, almost 18 kilometers per hour for a running humanoid. What allows for all that speed? It can't just be brute force, I imagine, right?
Not at all. It's actually a very complex combination. First, there are the mechanics, right? It needs to be lightweight, but also rigid to avoid losing energy. Second, the motors, the actuators. The H1 uses its own proprietary motors, the M107, which deliver a torque, think of it as the rotational force, of 360 Newton meters. That's a lot of force. It allows for very long strides and rapid acceleration.
I see. High torque for a long stride.
Right. And third, and perhaps most crucial, is the control system. It's a highly advanced software that manages the robot's entire body. It decides in milliseconds where and how each foot will touch the ground to maximize traction and maintain balance, especially for jumping over hurdles. It's almost like a human athlete, but everything is calculated.
Makes sense. And why does all this racing matter, besides being a tech showcase?
So this is a green light for a robotics market projected to reach nearly $400 billion by 2029. China clearly wants to lead the way. These games show that humanoids are moving beyond just the research phase. But are they already fully autonomous in these tasks? Can they go out and work on their own?
Whoa, hold on. We haven't reached that point yet. It's worth noting that much of what we saw in these games still has a teleoperation component, meaning a human is controlling it remotely or giving general commands. Full, robust autonomy, the kind that works day and night in a real environment, dealing with unforeseen events, managing its own battery, ensuring safety. That remains the great challenge. This race is a step, no doubt, but the marathon for true autonomy is still ongoing.
Understandable. It's an important step, but the journey is long. Well, from cutting-edge mechanical engineering, let's move to something completely different, quantum biology. Scientists in Chicago have managed to use a common fluorescent protein as if it were a qubit. For those who don't remember, a qubit is the basic unit of quantum computing. And the craziest part, they did it inside a living cell and at room temperature.
How is that possible? Yes, it sounds like science fiction, right? But the approach is very interesting. They took this protein, GFP, and used a technique called ODMR. Think of it as a pocket-sized MRI that uses light and microwaves. With this, They were able to read and write the quantum state of specific electrons within the protein.
Reading and writing the quantum state within the protein?
Exactly. And the master stroke is that this protein was made by the cell itself. They genetically modified the cell to produce its own native quantum sensor, so to speak. Instead of trying to insert a sensor inside, the cell manufactured it itself.
A native quantum sensor, that's incredible. And what's it for? Are they already thinking about quantum computing inside our cells?
Whoa, hang on. The focus here, at least for now, is more on sensing than on complex computation. The idea is to use this protein qubit as a tiny spy, to observe what's happening inside the cell with very high sensitivity. Imagine being able to detect subtle changes in the electric or magnetic field that could be an early sign of disease, or seeing how a protein folds, how it interacts with other molecules, things that are currently super difficult to see in real time and inside a living cell.
I get it. So it's more of a tool for biological research, for diagnostics, perhaps.
Exactly. For now, that's it. The sensitivity doesn't yet surpass the best quantum sensors we have, like those made of diamond. But the great advantage is this complete integration with the biological system. They're calling it biogenic quantum materials. It opens up a whole new door to study biology and, who knows, maybe even discover if important quantum phenomena are happening inside living beings. Something still heavily debated in science.
Fascinating. From quantum biology, we jump to neuroscience mixed with robotics. Now we have researchers in the United States who have connected a mini brain grown in a lab to a robot. Now that sounds like a movie.
It is a very notable advance, yes. But the term mini brain needs to be handled with some care, right? What they use are cerebral organoids. These are very simplified 3D structures of neural tissue that they grow from stem cells. What the research did was create a bridge, an interface using graphene to connect this organoid to a computer, and that computer in turn controlled a robot dog.
Graphene as the bridge. And how does this communication work? Does the organoid send signals to the robot?
That's more or less it. Through a technique they called GREMS. To simplify greatly, they use light to stimulate specific areas of the organoid. Graphene, being conductive and transparent, converts this light into very gentle electrical signals that the neurons understand. And the same graphene also serves to read the neuron's electrical response. So they close the loop. The robot detects an obstacle. A light signal stimulates the organoid. The neural response is read. The computer interprets it and sends a command for the robot to swerve.
And it happens fast, very fast. The whole cycle takes about 50 milliseconds. Wow, 50 milliseconds. And you said the organoid responds? Does it think? Does it learn anything from this?
Look, that's the most intriguing part and where we need to be most cautious. The researchers noticed that if they repeated the light stimuli, the organoid's response pattern changed over time. This suggests that the connections between the neurons were reorganizing themselves. It's a form of neuroplasticity, of learning at a cellular level.
Cellular learning is something a standard silicon chip doesn't do on its own, right? This opens up paths for thinking about prosthetics that adapt better to the body or robots that learn from experience in a more organic way.
But it's crucial to understand we are not talking about consciousness or complex thought. It's a biological tissue responding to stimuli and showing plasticity in a petri dish. Basically, the issues of its stability, of being able to replicate the results, and of course, the enormous ethical questions involved are gigantic. We are just at the very beginning of this exploration.
I see. It's more about exploring the potential of neural tissue as a different kind of processor that adapts. Very interesting. And speaking of things that come together, that assemble themselves, we also have modular robots that self-organize.
That's right. A very cool research project from Dartmouth. Imagine cubes like Lego blocks, but that can move on their own. Each cube has motors and strings inside. By tensioning these strings, it changes shape, can crawl, and grab onto other cubes. And then, together, they can form larger structures like a makeshift bridge or even a stretcher to carry something. The inspiration, they say, came from ants.
What an idea! And to build upwards, how do they overcome gravity?
Good question. They used a drone as a sort of aerial crane. The drone helped position the cubes in higher places, allowing them to build 3D structures. They even simulated a search and rescue scenario, with the drone helping to locate a module that had been injured, so to speak.
Using a drone for support is brilliant.
Exactly. The great advantage of this type of robot is its versatility, right? With the same basic set of cubes, you can create totally different structures. You can imagine applications in civil defense to create rapid access in disasters or even in construction, like scaffolding that reconfigures itself.
Truly versatile. Changing gears a bit to take a breather from this complex robotics and biology, a gadget has appeared that's catching attention. The DID, a keyboard that folds into a touchscreen. What do you mean?
Exactly that. It's a portable keyboard. You fold it to store it. When you open it, the inside reveals a 12.8-inch touchscreen. Then you connect it via USB-C to your laptop or tablet, and it works as a second monitor.
Interesting for people who work while traveling.
Yes. Perfect for anyone who needs more screen real estate for, say, notes, code, or a video timeline without constantly switching windows on their main computer.
Seems useful indeed. What about the specs? Any significant limitations?
Well, the screen is a 60 Hz IPS panel with 10-point touch, which is good, but the resolution is 720p. The keyboard is a scissor switch type with RGB lighting. The body is aluminum, but it weighs about 800 grams. The connection is simple, just one USB-C cable for both video and power. But to use it with Android, the phone needs to support DisplayPort mode.
720p might be a bit low for some tasks, right?
It could be, yes, it really depends on the use case. And the other issue is that it started as a Kickstarter crowdfunding project. So there's always that associated risk, delays in delivery, perhaps some changes to the final product. That's the price of innovation via crowdfunding. The estimated price is around $500.
Understood. It's a cool idea, but with its caveats. Well, returning to AI and cutting-edge robotics, we've been hearing a lot about Figure AI. That's the company that received heavy investments from people like Bill Gates and Jeff Bezos. Now they've raised another $405 million for what?
For something called Fields Foundation Models, or FFMS. They are large artificial intelligence models. Think along the lines of LLMS, like ChatGPT, that generate text, but these are focused specifically on robotics. And the big idea, what's attracting so much money, is their approach. They want robots to understand and reason about the world using physics.
With physics built in?
Exactly. Instead of just relying on recognizing patterns in images or preloaded maps, these models incorporate physical principles like gravity, friction, and stability to make decisions in real time. The idea is that the robot understands that if it leans too far on a ramp, it will slip, or that it needs to apply more force to lift something heavy, even without having seen that exact situation before.
Makes perfect sense. It's a step towards that robust autonomy you mentioned earlier, right? The kind we still need to see robots actually working out in the world. Instead of specific rules, it would have a more fundamental understanding to adapt.
This could greatly accelerate the practical use of advanced robots in industry. Think of a construction site, a somewhat chaotic warehouse. Physics-based I would help the robot deal with the unexpected more robustly. And these models run directly on the robot at the edge without relying on a constant connection to the cloud.
This need to operate in complex, unpredictable environments leads me directly to our final topic, which is perhaps the most challenging and unknown environment of all, the deep ocean. We're talking about deep sea mining, specifically in an area called the Clarion-Clipperton Zone in the Pacific. What's at stake there?
This zone, the CCZ, is over 4,000 meters deep. There, you find vast plains covered in polymetallic nodules. They're like potato-sized rocks that are very rich in nickel, copper, cobalt, and manganese.
Essential metals for the energy transition, right? Batteries, wind power.
Exactly. The company's idea is to use giant robotic vehicles like underwater vacuum cleaners to suck up these nodules. Proponents argue that the impact would be less than mining on land. No deforestation, no tailings dams.
But what are the concerns from the other side?
First, we know very, very little about life in these depths. It's one of the least explored ecosystems on Earth. These nodules take millions of years to form and are the only hard substrate where certain organisms can attach themselves to live. Many haven't even been described by science yet. Removing the nodules means permanently removing their habitat.
And is there any other impact besides removing the habitat?
Yes. The very act of collecting the nodules will kick up clouds of very fine sediment from the seafloor. These are called plumes, and these plumes can travel for kilometers, suffocating filter-feeding organisms like cold water corals and sponges, and altering the water chemistry. There's also the concern of releasing carbon that has been stored for centuries in that sediment.
Is it known how long-lasting this impact could be?
Well, there was an old experiment from 1979 in this same zone. The tracks left on the seafloor by that test are still visible today, more than 40 years later. And the life that directly depended on the nodules in that small area simply has not returned.
Wow, that's why many scientists and NGOs are calling for a moratorium on commercial mining, or at least a pause for more research.
Exactly. The regulation of this is in the hands of an international body, the ISA, but there's a clear tension between the pressure to start exploiting these resources, which are considered the common heritage of humankind, and the precautionary principle of protecting an environment we barely know.
It's a huge dilemma, isn't it? We need these metals for a more sustainable future on land, but at what cost in the deep sea?
Exactly. That's the point. There's no such thing as zero-impact mining, not on land or at sea. The question is what impacts we are willing to accept. If this mining moves forward, the very least to expect is large, untouched protected areas, extremely rigorous environmental monitoring, and full transparency. The technology to mine is almost ready, but the science to understand the consequences is still far behind.
What a deep journey we took today, huh? From the almost athletic speed of humanoid robots, through the incredible ability to use biology at a quantum level and connect brain tissue to machines, all the way to the gigantic challenges of seeking resources in one of the most remote and fragile places on the planet. We saw how engineering, biology, AI, and robotics are all intertwining.
Indeed. And it leaves us with a final thought, perhaps connecting many of these points. We are in a race for resources like these deep sea metals, partly to enable these very new technologies. At the same time, we're developing ever smarter robots to operate in these extreme environments and interfaces that are beginning to blur the line between the biological and the artificial. The big question that remains is how we can balance this relentless pursuit of innovation with long-term responsibility for the systems we inevitably impact, whether they be the delicate deep sea ecosystems, the biological systems we're starting to manipulate, or even the future interactions between us and these increasingly autonomous machines we are creating.
The video isn't over yet. The conversation keeps going in the comments below. If you enjoyed this video, I'd like to invite you to become a member and be sure to give it a like. I'll put another video for you to watch right up here on the right.